Alright, so now we've mastered solving axial force, shear, and moment at a point. It's time to go ahead and look at solving for these values along the entire length of the member. Now, so far in our course, we've looked at axial force diagrams and torsion diagrams, and that, gives you the values at all points along the length. And so just like that, we also want to review how do we draw axial force diagrams and then shear and moment diagrams for beam members along the entire length so that we can find where the maximum and minimum values of those forces occur. Alright, so the second method we're going to explore is solving for axial force, shear, and moment diagrams by using equilibrium to get a function along the length. So step 1, compute reactions if necessary. Again, I would consider step 1 and 2. So 2 is going to be determine the number of intervals for analysis. And think even with 3, depending upon where you make that cut, whether or not the reactions are going to be necessary. 3 is to cut the structure at the location within each interval and draw the free body diagram. Again, make sure to properly draw the internal forces at the cut and maintain consistent units. And lastly, we'll use equilibrium to solve for functions now of axial force, shear, and moment. All right, so let's go ahead and walk through these steps. So this is a little bit of a time-consuming problem, so get ready. But hopefully you'll have a good understanding of how to do it after this. So I'm going to go ahead and add my reactions at A. So we have AY, AX, and the moment at A. And, step 1 says to solve for the reactions. And in this case, we're going to need them because we're going to be setting up our X coordinate system starting at A and moving from left to right. And so therefore, we're going to need these reactions at the very start or at the origin of our X coordinate system. All right, so let's go ahead and get these reactions. Summing forces in the x direction, we get AX. We have a plus 14 kips at C and a minus 9 kips at B equals 0. So AX ends up being a negative 5 kips. Again, when we're talking about external forces like support reactions, the negative 5 just means we drew the arrow in the wrong direction, or AX should be oriented to the left. Next, we'll sum forces in the y direction. So this will give us AY. And now we have to take into account this distributed load. And if we recall from statics, we would come up with an equivalent force, a statically equivalent force, whenever we had distributed loads. And that statically equivalent resultant force was applied through the center of gravity of whatever distributed load shape we have. In this case, we have a triangle. So our resultant force will act a distance of 2/3 from the left-hand side or 1/3 from the right-hand side or the tall side of the triangle. So that's 20 feet from the left-hand side and 10 feet from the right-hand side. So just a little bit to the left of point C, even though the picture doesn't show that well. For my sum forces equation, I'm just simply going to put sum forces in the y as AY minus R equals 0. And then we have to solve for R. R is the area under that curve, 1/2 the base of 30 feet times the height of 2 kips per feet. Keeping my units, we see that that will come out to 30 kips. And so we have a value of force, which is good. So if I go ahead and solve for AY, AY is equal to 30 kips. And that'll be acting upward or in the right direction as I drew AY at my reactions. Lastly, we'll sum our moments at point A. And so in doing this, we have the fixed end moment MA. And then we have a minus R times 20 feet. The 14 kips and the 9 kips will intersect point A, so they don't contribute to the moment. Solving for MA, we now have R was 30 kips times 20 feet, so that's 600 kip feet. Positive, so that means the direction I drew MA was correct, or that it's acting counterclockwise at the reaction point. All right, so step one's done. We got the reaction solved. Next, we have to determine the number of intervals. This takes a little bit of practice. Basically, you just want to find intervals where loads significantly change. So in this case, we see that, from A to B, the distributed load is pretty much uniform. But we do have at point C, we have a switching in the axial forces. So I would say from A to C, we have our first interval, and then from C to B is our second interval. And so we'll go ahead and make that clear. For step 2, we want to define our intervals. So let me fix the color there. Step 2, we'll define our intervals. And so we have 2 intervals that we identified, namely from A to C and C to B. All right, moving along to step 3. We are asked to cut the structure at a location X within each interval and then draw a free body diagram. And then we can move on to step 4, which will actually be using that free body diagram using equilibrium to solve the problem. So I don't really have space on this page for step 3, so we're going to have to go ahead and put step 3 on the next page. But before I do that, I want to go ahead and draw my cut on my first interval. So make sure you cut in the interval, not at A or not at C, but somewhere arbitrarily in the middle. And so I'm going to define my coordinate system X starting from point A and then going to the right. I'm just going to cut anywhere, somewhere between A and C. And I'm going to loop it back around my origin since I have to be careful there with my X coordinate system. And now I'm going to take this circled free body diagram and I will draw this on the next page. All right, so I'm going to get my free body diagram in my cut in interval AC sketched out. So in that sketch, I have a beam. It has a cut. It has a distributed load that starts at 0 and goes up to some number. I'm not really sure what number that is because I'm at a random point, remember. At my reaction at the left, I have my forces, my reaction forces, AY 30 kips, AX was 5 kips to the left. And my fixed end moment was counterclockwise, a value of 600 kip feet. I also have my forces on the right-hand side, and that's a right-hand cut going back to my sign convention. So my axial force acts to the right, my shear force acts downwards, and my moment is counterclockwise. And because I'm at an arbitrary point X, I have all of those internal forces as functions. Finally, I need to somehow take care of this distributed load. And so I'm at some arbitrary point X, that's my dimension. And I need to handle what value does my distributed load that's drawn here in orange, what is the peak value on the right-hand side? Well, simply put, I can just say that this is a function. omega x. And I'll treat the orange line, this sloped, this line sloping up and to the right, as just some linear line in a Cartesian coordinate system. So let's go ahead and take a look at a line in algebra, right? Y equals mx plus b. But b is my y-intercept, which is 0 because at x equals 0, because I define my coordinate system, my origin at point A. At the origin, my intercept is 0 because omega of x has a value of 0 there. So that just basically means I need to find the slope of this line. I know from my original picture that it goes up to a value of 2 kips per feet after a length of 30 feet. So that gives me a slope of 1 over 15. And so y equals 1/15 x, or in this case, omega of x is going to equal 1/15 x. So that's the height at any point from along the length of this beam. I think I have everything I need to go ahead and solve this. So I'll go ahead and get started on my equilibrium equations. I'll start as I typically do with some forces in the x direction. Remember, you can go in whatever order you would like. You have 3 equations of equilibrium here. But summing force in my x direction, I'll get a -5 kips. And then the only thing acting in the x direction is my positive n of x force. And so this basically just tells me n of x is 5 kips. Positive 5 kips, which means it's acting in tension. And again, I can draw my little element in tension. And so basically at all points from 0 up to 20.2, or all points on interval AC, my axial force is 5 kips tension. Next, I'll sum forces in the y direction. This gives me 30 kips minus v of x at my cut. And then minus, and I need the resultant of this distributed load again. So let me go ahead and color that in, and this distributed load is different than the last one. It's same principles. I'll put in my resultant force R so that I distinguish it from the previous one. Let me call this R2. And that'll be located at distance 1/3 from the tall side. And if my total distance is x, that means x over 3 from the right, or 2/3 x from the left-hand side. And now I have to come up with a value of R2. Remember, R2 is just the area under the distributed load curve. So to figure out that value, R2 is going to be 1/2 times the base times the height. So 1/2 times x, which is the base, and then the height, which is 1/15 x, or the value of omega x at the right-hand side of the triangle. And don't really be scared with these x's, it's algebra. So I do the multiplication, it's 1/30 x squared. All right, if I return back to my equilibrium equations, rather than writing this in directly, I like to start by just saying like 30 kips minus v of x minus R2, so that that's clear and our equation equals 0 because that's a force. And now I'll go through and I'll substitute. So this gives us 30 kips minus v of x minus, now I'll substitute 1/30 x squared. And now I need to solve for the function v of x. Bring those other two to the, bring v of x to the right-hand side, and we'll get 30 kips minus 1/30 x squared. So that's my function. I can't really draw my little elements this time because I don't really know if it's positive or negative because, of course, it's an algebraic equation. All right, lastly, we'll sum moments. I'll do it about the cut to kind of simplify things. That'll get rid of n of x and v of x in our moment equation. Still leaves m of x, which is what we're looking to find. And then if I keep looking at forces, I see that I have a plus r2 times the distance from the cut, x over 3. A of x doesn't contribute to the moment. I get a 30 kips times x, and that's going to be negative because it's going to act counterclockwise relative to my cut. Or sorry, clockwise relative to my cut. And then lastly, I add in a 600 kip feet for the fixed end moment at A. Again, I just have some math to do and some substitution. M of x, I substitute 1/30 x squared for r2 times x over 3 minus 30x plus 600 equals 0. So m of x, bringing everything to the other side, gives us minus 1/90 x cubed minus or plus 30x minus 600. And that now is my equation for the moment at any point between points A and C. Now I want to plot these diagrams. So I was interested in plotting the axial force, shear, and moment diagrams. So I'm going to go to the previous page where I have my graph set up to plot these values. You want step force tacked in here. Let's just add that into the notes so that they're complete. All right, so using those functions, I'm going to plot my axial force first. We said it was 5 kips. It didn't change between A and C, so it was a constant 5 kips of tension between those 2 points. Next, I'll add my shear. I said my shear force was 30 minus 1/30 x squared. So if I plug in 0 for x, that'll give me 30 kips. And now I need to figure out what it is at point C. So at point C is at a value of x equals 20.2 feet. And so if I plug that into my function that I solved, I get a value of 16.40 kips. So let's just make that clear. If I come back to the next page, V, I'm looking to get V of 20.2 because this is at point C. I plug in 20.2 for x, and I solve, I get 16.40 kips. Positive shear. Likewise, I can do the same for moment. M of 0 is going to give me negative 600, and then M of 20.2 is going to give me negative 85.58. That's going to be units of kips times feet. So let me go ahead and complete my plots here. So V of x is a quadratic equation, so I have some sort of parabola acting here between points A and C. Now I need to get my moment values. My moment at M of 0, I plug that into my function and I get negative 600. And then when I plugged in 20.2, I had negative 85.58. And let me correct that. Negative 85.58 kip feet. Sorry, I'm a little sloppy there. I'll make it clear. Okay, this is a cubic function. You can use a graphing calculator, your computer or something to plot this cubic function, but it should look something like that between those 2 points. All right, finally, we need to look at this for the next segment. So kind of the last step, step number 5, or, is just to repeat steps 3 and 4 for every interval that you identified in step 2. So in this problem, we're going to have to repeat steps 3 and 4 for interval C to B. And so what exactly does that look like? Well, if we go back to our problem, we'll see that the only thing that really changes for interval C to B is the axial force. Our linear function remains the same. It's still a linear function it's a continuous linear function on the interval AB. So basically all we have to look at is the difference on CB is the fact that the axial forces change. Maybe we can see that a little bit clearer by looking at the picture itself. We can go ahead and we can draw the free body diagram for a cut through CB. So if you were going to solve the problem, you would do this again. Make sure you circle all the way back to the origin again. And then we would draw a free body diagram of this cut on segment CB, and we would do all the steps that we did previously. But you'll find that the shear equation and the moment equation will remain the same. The only thing that changes is the axial force. And if you go back to the beginning of our mechanics and materials class, I think you can quickly identify that axial force on segment CB needs to be a -9 kips in compression. So since the shear and moment equations don't really change, just continue those functions. And then ultimately at the end of the beam, they both have to be 0 because we have no load and we have no support at that location. I'll put in my positive sign conventions and my graphs, my diagrams are complete. The final part of the problem asked us to just use the axial force to calculate the deflection at B. So basically we're looking for the axial deflection at B. So this is a good review from the very beginning of our mechanics of materials class. Just remember using our PL over EA equation to solve for axial force at B. So if I go ahead and I calculate the axial force at B, my first step would be to quickly come up with a kinematics condition for the deflection at B. So that kinematics condition would be delta B equals delta A plus delta C relative to point A plus delta B relative to point C. Delta A is going to be 0. I think that last term should be delta B relative to point C. And so that's going to give me 0. On segment AC, I have a positive 5 kips times length of 20.2 feet. Just recall our delta equals PL over AE equation. So we have 5 kips times 20.2 feet. I'll put that into inches. And then divide that by the modulus of elasticity in the area. In this case, the problem gave them to us as 10 inches squared for the area, and then E of 29,000 KSI. And so this is basically all the stuff for segment AC. Next, we need to do segment BC. Segment BC we found to be in -9 kips of compression. The length of BC is only 9.8 feet long. Convert that into inches. Same area, same modulus of elasticity. All right, and then put our calculators to work. You should solve that the deflection at B, delta B, is 0.000530 inches. Positive number indicating stretch to the right. All right, I hope this has been pretty instructive for method of equilibrium. We'll take a look at another method next time.